Hello everyone. Welcome to the 11th lecture on partial differentiation. This is in continuation to the lecture number 10 of partial differentiation. In lecture number 10, we have discussed about maxima minima of functions of two variables. In this lecture, we'll discuss some example of maxima and minima of functions of two variables. Before proceeding to the examples of maxima and minima, let us recall the working rule for maxima minima. Let z is equal to f of xy be a function of two variables x and y. First step is to evaluate the partial derivative of the function with respect to x and partial derivative of the function with respect to y. Then the next step is to equate the partial derivative of the function with respect to x and with respect to y to 0. In this process, we will get two equations. If we put del f by del x is equal to 0 and del f by del y is equal to 0, we have two equations. Now, by solving that two equation, we will obtain the values of x and y. Now, the values what we get x and y by solving these two equations, that is our critical point AB. Now, evaluate the higher order derivatives RST at that point AB, where r is the second order partial derivative of the function with respect to x, that is del square f divided by del x square, and s is our second order mixed partial derivative, that is del square f divided by del x del y, and our t is second order partial derivative of the function with respect to y, that is del square f divided by del y square. Now, if rt minus s square is positive, then the function f of xy has a maximum value at that point AB if r is negative, and the function has a minimum value at the point AB if r is positive. If rt minus s square is negative, then the function f of xy has a saddle point at that point AB. If rt minus s square is 0, then further investigation is required to find out maxima minima. So this is the working rule for finding out maxima minima of a function of two variables. Now let us discuss some examples on it. If the question is find out the extreme values of the function f of xy is equal to minus of x square plus y square plus twice x plus y plus 1. Now here our function f of xy is minus x square minus y square plus 2x plus 2y plus 2. Now let us find out the partial derivative of this function with respect to x. That means del f by del x. That is del by del x of fx. Now our function is this. Since we are partially differentiating the function with respect to x, y is treated as a constant. So we have here the derivative of minus x square is minus 2x. Derivative of y square is 0 because y is treated as a constant. Derivative of 2x is 2. Derivative of 2y is 0. And derivative of 2 is 0. So del f by del x is minus 2x plus 2. Similarly, partial derivative of the function with respect to y is minus 2y plus 2. Because here x is treated as a constant. So derivative of this x square is 0. Derivative of 2x is 0. And derivative of 2 is 0. So derivative of minus y square is minus 2y plus derivative of 2y is 2. So we have minus 2y plus 2. Now equating del f by del x and del f by del y to 0, we have these two equations. Our del f by del x is minus 2x plus 2. So minus 2x plus 2 is equal to 0. And our del f by del y is minus 2y plus 2. So minus 2y plus 2 is equal to 0. Now if we solve these two equations, we will get values of x and y. Now solving these two equations, we have x is equal to 1 and y is equal to 1. So our critical point is 1, 1. So 1, 1 may be a point of maxima or point of minima. That means 1, 1 may be a point where the function has a maximum value or a minimum value. Let us check it. Now to check that whether it has a maximum value or a minimum value at this point 1, 1, we have to find out the higher order partial derivatives, RST. Now, our R is del square f divided by del x square, that is del by del x of del f by del x. And we have del f by del x with us, that is minus 2x plus 2. So, partial derivative of this with respect to x is minus 2. And our S is del square f divided by del x del y, that is del by del x of del f by del y. And our del f by del y is minus 2y plus 2. Now differentiating this minus 2y plus 2 with respect to x, we have 0 because here both are constant. Here y is treated as a constant, so this is constant and 2 is constant. So the derivative of this minus 2y plus 2 with respect to x is 0. Now partial derivative t, that is del square f divided by del y square, is del by del y of del f by del y. And our del f by del y is minus 2y plus 2. Now differentiating this with respect to y, we have minus 2. Derivative of minus 2y is minus 2. And derivative of 2 is 0. So we have minus 2 here. So our r is minus 2, s is 0, and t is minus 2. So now let us find out what is RT minus H square. Our R is minus 2, our T is minus 2, and our S is 0. So minus 2 into minus 2 minus 0, which is equal to 4. Here we have seen that this is a positive number. RT minus H square is positive. We know that if RT minus H square is positive, then the function has a minimum value if R is positive, and the function has a maximum value if R is negative. Now here we have RT minus S square is positive. Now what about the value of R? Here we can see that the value of R is minus 2, which is negative. So the function f of xy has a maximum value at 1, 1. Because at 1, 1, R is negative. Here R is always negative for any values of x and y. So at 1, 1, it is negative. So the function has a maximum value at 1, 1. Now here we have another example. Find out the maximum and minimum values of the function f of xy is equal to x cube plus y cube minus 3axy. Here our a is a positive constant. Now our function is x cube plus y cube minus 3axy. Let us find out the partial derivative of this function with respect to x and with respect to y. Now the partial derivative of the function with respect to x, del f by del x, is equal to del by del x of the function x cube plus y cube minus 3xy, which is equal to 3x square minus 3ay, because here y cube is a constant. It is derivative of this y cube is 0. Similarly, del f by del y is equal to del by del y of x cube plus y cube minus 3axy, which is equal to 3y square minus 3ax. Now equating the partial derivative of the function with respect to x and the partial derivative of the function with respect to y to 0, that means equating del f by del x is equal to 0 and del f by del y to 0, we have two equations. 3x square minus 3ay is equal to 0 and 3y square minus 3ax is equal to 0. So we have these two equations with us. Now solving these two equations, we will get values of x and y. Now from 1 we have 3x square is equal to 3y, because 3x square minus 3ay is equal to 0, which can be written as 3x square is equal to 3ay. This implies y is equal to x square divided by a. 3 get cancelled with each other. Now y is equal to x square divided by a. Let us denote it as equation 3. Now putting the value of y from equation 3 in 2, we have this. Because our equation 2 is 3y square minus 3ax is equal to 0. And our value of y in equation 3 is x square divided by a. Now putting x square divided by in the place of y, we have 3 into x square divided by a square minus 3ax is equal to 0. This implies x4 divided by a square minus ax is equal to 0. This implies x4 minus aqx is equal to 0. By taking x common, we have x into x cube minus aq is equal to 0. This x into x cube minus aq is equal to 0 if either x is equal to 0 or x is equal to a. So we have two values of x. Either x is equal to 0 or x is equal to a. If x is equal to 0, then what is the value of y? We can get it from equation 1. By putting x is equal to 0 in equation 1, we have y is equal to 0. If we put x is equal to 0 in equation 1, we have y is equal to 0. Similarly, if we put x is equal to a in equation 1, we have 3a square minus 3a y is equal to 0. So our y is a. So we have now x is equal to 0, y is equal to 0. When x is equal to a, y is equal to a. So we have two critical points here, 0, 0 and a. So by the necessary condition, point 0, 0 and 1, 1 may be the point where the function have extreme values. Let us check. To check whether these point 0, 0 and a are extreme points or not, let us evaluate the higher order partial derivative RST. Now our R is equal to del square f divided by del x square, that is del by del x of del f by del x, that is del by del x of del f by del x is our 3x square minus 3ay. So differentiating 3x square minus 3ay with respect to x, we have 6x. Because 3ay is a constant, we are differentiating this with respect to x, so y is constant. Now s is equal to del square f divided by del x del y, that is del by del x of del f by del y. Now our del f by del y is 3y square minus 3ax. Now partially differentiating this 3y square minus 3ax with respect to x, we have minus 3a because 3y square is a constant. Now t is equal to del square f divided by del y square, that is del by del y of del f by del y. That means partial derivative of 3y square minus 3ax with respect to y, which is 6y. Now our RST are 6x minus 3a and 6y. Now let us evaluate what are the values of RST at point 0, 0. At 0, 0, R is 0 because x is 0, so 6 into 0 is 0. At 0, 0, S is minus 3a. And at 0, 0, T is again 0 because y is 0. So we have R is equal to 0, S is equal to minus 3a and T is equal to 0 at 0, 0. Now what is RT minus S square? Our RT minus S square is 0 minus 3a square, that is minus of 9a square. Here we have taken a as a positive constant. So minus 9a square is a negative number. Hence the function f of xy doesn't have an extreme value at the point 0, 0 because here rt minus s square is negative. By the working rule, we know that if rt minus s square is negative, then the function doesn't have an extreme value at the point 0, 0. Now at the point a, our value of r is 6 into a because at a x is a. So 6a. Similarly, the value of s at a is minus 3a. And the value of t at this point a is 6a because our y is 0. Y is a. So 6a. Now the value of rt minus s square is, our r is 6a into t is 6a minus s square. Our s is minus 3a square. That is 36a square minus 9a square, which is 27a square. It is a positive number. We know that if rt minus a square is positive, then the function has a maximum value at that point if r is negative, and the function has a minimum value if r is positive. Since at rt minus s square and r both are positive, the function f of xy has a minimum value at aa. So the minimum value of the function is faa. So just we have replaced x and y by aa, which is our minus aq. This is the minimum value of the function. Now here we have one more example. Let the function f of xy is equal to x cube plus 3xy square minus 15x square minus 15y square plus 72x. Find the maximum and minimum value of the function f of xy. Now here we have the function. Let us find out the partial derivative of this function with respect to x and with respect to y. Now the partial derivative of this function with respect to x is 3x square plus 3y square minus 30x plus 72. Because here we are differentiating the function with respect to x. So y is treated as a constant. From the first term we get 3x square. From the second term we get 3y square. From the third term we get minus 30x. Fourth term is a constant, so derivative is 0. And from the fifth term we get 72. So we have 3x square plus 3y square minus 30x plus 72. Similarly, the partial derivative with respect to y is 6xy minus 30x. Now equating del f by del x and del f by del y to 0, we have two equations. Now, what is del f by del x? If we equate del f by del x to 0, we have this. 3x square plus 3y square minus 30x plus 72 is equal to 0. Now equating del f by del y to 0, we have 6xy minus 30y is equal to 0. From here we can get that by taking 6y common, we have 6y into x minus 5 is equal to 0. This is equal to 0 if either y is equal to 0 or x is equal to 5. So now we have two values, either y is equal to 0 or x is equal to 5. Then only 6y into 5 x minus 5 will become 0. Now if we put y is equal to 0 in equation 1, then equation 1 becomes 3x square minus 30x plus 72 is equal to 0. Because if we put y is equal to 0, this term 3y square will become 0. So we have 3x square minus 30x plus 72 is equal to 0. Now taking 3 common, we have 3 into x square minus 10x plus 24 is equal to 0, which can be written as x square minus 10x plus 24 is equal to 0, which is nothing but x minus 4 into x minus 6 is equal to 0. So here we have either x is equal to 4 or x is equal to 6. So if y is equal to 0, then we have either x is equal to 4 or x is equal to 6. So now we have two critical points. For x is equal to 4, y 0, x is equal to 6 and y 0. So 4 0 and 6 0 are two critical points here for y is equal to 0. Now if y is equal to, if x is equal to 5, if we put x is equal to 5 in equation 1, we'll get two more points. So if x is equal to 5, then from equation 1, we get 75 plus 3y square minus 150 plus 72 is equal to 0. Because x is equal to 5, here we have equation 1 with us. If x is equal to 5, then x square is 25 into 3 is 75 plus 3y square minus 30 into x is our 5. So 30 into 5 is 150 plus 72 is equal to 0. Now we have 75 plus 72, that is 147 minus 150, which is our minus 3. So 3y square minus 3 is equal to 0. Now taking 3 common, we have y square minus 1 is equal to 0. So either y is equal to 1 or y is minus 1. So here we have seen that if x is equal to 5, then the value of y is either 1 or minus 1. So here we have two more points. For x is equal to 5, either the value of y is 1 or minus 1. So we have 5 1 and 5 minus 1 are two critical points. So in the first case, we got two critical points, 4 0 and 6 0. And in the second case, we get two more critical points, 5 1, 5 minus 1. Therefore, four critical points of the function are 6 0, 4 0, 5 1, 5 minus 1. Now we have to check one by one at which point the function has extreme values. Let us now evaluate the higher order partial derivatives. Now the higher order partial derivatives r is equal to del square f divided by del x square, that is del by del x of del f by del x. Now del f by del x is 3x square plus 3y square minus 30x plus 72, and the partial derivative of this with respect to x is 6x minus 30. Similarly, s is equal to del square f divided by del x del y, that is del by del x of del f by del y, and del f by del y is 6xy minus 30y. Now partial derivative of this is 6y. Similarly, t is equal to del square f divided by del y square, that is del by del y of del f by del y, and our del f by del y is this. Now partial derivative of this with respect to y is 6x minus 30. Now our r is 6x minus 30, our s is 6y, and t is 6x minus 30. Now let us evaluate these r, s, t at all those 4 points. So at the first point 4 0, value of r is, our r is 6x minus 30. So 6 into x is our 4 minus 30, that is equal to 24 minus 30 is equal to minus 6. Our s is 6y, and here we are finding out the value of s at 4 0. So our y is 0 here. So 6 into 0 is 0. Now our t is 6x minus 30. Our x is 4 and y is 0. So 6x minus 30 is equal to 24 minus 30 is equal to minus 6. So at this point 4 0, value of r is minus 6, value of s is 0, value of t is minus s. Now what is rt minus s square? Now rt minus s square is minus 6 into minus 6 minus 0, that is 36, which is a positive number. So here rt minus s square is positive. Since rt minus s square is positive and r is negative at this point, the function has a maximum value at this point. Here our r is minus 6 at this point, which is negative, and the value of rt minus s square is positive. So the function has a maximum value at the point 4 0. Now let us evaluate RST at other points. Now at the point 6 0, the value of R is 6x. Our x is 6. 6 into 6 minus 30, which is 36 minus 30, which is 6. Our S is 6y. So here y is 0. So 6 into 0 is 0. Our t is 6x minus 30. And here our x is 6. So 6 into 6 minus 30. That is equal to 36 minus 30, which is 6. Now rt minus s square is 36, which is positive, and here r is positive. So the function has a minimum value at this point 6 0, because here rt minus s square is positive and r is positive at this point. So at this point 6 0, the function has a minimum value. Now at 5 1, value of r is 0 S is 6, T is 0. So RT minus S square is minus 36. We know that if RT minus S square is negative at any point, then that point is neither a point of maxima nor a point of minima. Rather, the point is known as a saddle point. So here the point 5, 1 is a saddle point. Now let us check at the last point, which is our 5 minus 1. At 5 minus 1, value of R is 0, value of S is minus 6, value of T is 0. So RT minus S square is minus 36, which is negative. So here also the point 5 minus 1 is a saddle point. This is all about in this lecture. In the next lecture, we'll discuss some other concepts of differential calculus.